Se on taas ligipäätä, että varmaan. Right, I think I forgot last time to send you the screens. And let me do it just before we start. Sorry about that. Let me try today to send immediately after I finish. So it will be easy. And now I installed update of that software. Let us hope it will work better today. And I guess we can start then. And last time we finished with the fractal dimension of incompressible flows, something like that. And then there was a homework. Did you manage to do it?
Yes.
And what is the result? What you got? Let me see. No, that's correct. That's not correct. It's tempting to write that, but that's not correct. Now, Tooma, did you manage to set homework with the Gaston dust dimension? Did you manage to get it?
Yeah, unfortunately, I was submitting a paper for publication this week, so I didn't have time to get around to it. But I'll try this week.
Okay. So what shall we do? Shall we? Okay. Let us do it in one way, but there is another way of doing it as well. So let us do it using mass dimension, but there is also the way of doing it using the box counting dimension. So let me leave the box counting method for you to do, which is a little more, or maybe the other way around, because box counting method is a little more tricky than the mass dimension. So maybe we'll do first mass dimension, and then I will left the other way around. We'll do it using box counting. Then you'll be trying doing it with the mass dimension by yourself, which is easier. But then you know what is the answer. Tudor, did you manage to get the fractal dimension of that count?
I got it. I got the answer arc sine of 2 divided by log 2. So I got 1 plus 2 to the k equals 4 to the k.
I cannot say I have a different form. We can check it later numerically or something. Okay, so first, so we have a second. And then we got into 2, and again into 2, and this part throw out. And then we continue, but let us start doing first. If we take our box, is this thing here. So how many boxes do we need to cover the fractal counter dust? No. Tell me 1, right? This, yeah, we need 1 exactly. Now let us make it into 2 times smaller. And how many now? 2, right? 2. Now let us make it even 2 times smaller. And how many now? 3.
Professor Jurla, I can't see what you're writing.
Sorry?
I can't see what you're writing. I don't think it's being shared to the Zoom.
Oh, right. Yeah, sorry. Thanks for reminding. Yeah, I forgot to share the screen. Thank you. Right. Okay, now it's better, I guess.
Perfect. Yes, thank you.
Okay, yeah. So quarter size, we need 3. And now, and yes, this goes to cover. Let me somehow mark it. Okay, this one goes here, another goes here, and another goes here. Okay. Now let us take it 1/8. Maybe we start now needing a little be more specific here and also cut here out.
It's 5 regardless.
Regardless, it's 5. Right. It is 5 indeed. Okay, and now the next one. How many? Huh? Yeah, tell me.
I don't know.
You don't know? Okay. Let us see. Well. Do we need
8? 8?
8.
Is it full Fibonacci?
Yeah, it is Fibonacci.
Oh.
Okay. So now we can probably stop here. You need to just convince yourself that's indeed Fibonacci. Do you know, guys, Fibonacci?
Yeah.
Yeah.
Okay, so it's a Fibonacci sequence.
So it's like 1 plus square root of 5/2, or?
Okay, now guys, the next question is, do you know how to calculate Fibonacci number? So we need to limit the Fibonacci number, so a big N. So do you know what it is? Do you know how to calculate Fibonacci?
I know how to do it.
Tudor knows. What about the rest? Toma, do you know how to calculate Fibonacci?
I mean, it's the sum of the previous 2 numbers is the next number.
Yeah, that's right. But if we want to have nth member, do you need to calculate just by summing, or is there another way?
It's multiply n times. That's so much easier than summing.
All right. So, okay, you probably don't know. But maybe Tudor knows, but because it has some math background. So we have a sequence that Fibonacci n is Fibonacci n minus 1 plus Fibonacci n minus 2. And now, if you were to do some numerical simulations, this would be something like similar to taking derivatives. Time derivative is just difference between 2 members, right? So it kind of reminds you taking derivatives, and in that case, we'd have something like differential equation and linear and second order at that. So how do we solve a linear differential equation of such kind? We have characteristic equations, isn't it? So here we do the same. We look for solutions in exponential form, meaning that we search for Fn equals certain number a to the power of n and plug in. And then we obtain a to the power of n equals a to the power of n minus 1 plus a to the power of n minus 2. And then a to the power of n cancels out, and we obtain a square equals a plus 1. Quadratic equation. And then, we can solve probably. So a comes out as 0.5 plus minus square root 1.25, I guess. Or you can rewrite it like 1 plus minus
Root of 5.
5, square root of 5, but something like that.
Yeah.
Okay, good. Now, we have two solutions, plus and minus. And we have also our initial conditions. We know that actually Fibonacci 0 is first two are postulated as we can postulate 1 0 and 1, for instance. F0 is F0 is 0, F1 is 1. Okay, so we know what is A now. We have two options. But of course, here, similar to linear differential equation, superposition principle works. So any linear combination of those two solutions is also a solution. And so we are looking for f in a form f equals f of fn equals okay, divided by 2 isn't even needed because 2 goes. No, 2 is still needed definitely.
Yeah, it goes into the
2
power.
is needed, but yeah, so here is a certain factor c1, 1 plus square root of 5 divided by 2 to the power of n plus c2, 1 minus square root of 5 over 2 to the power of n. And then we use n equal to 0 to conclude that c1 equals to minus c2. So that our fn obtained form fn equals, now we can just use a single c, c multiplied by 1 plus square root of 5 over 2 to the power of n minus 1 minus square root of 5 over 2 to the power of n. And if n equals to 1, so we 1's cancel out. 1 cancels out, and what is left is square root 2 square root of 5 divided by 2, which is square root of 5, isn't it? Is c times square root of 5, and from here we conclude that c is 1 divided by square root of 5. And that's it. That's how we do it. Okay. And now we have Fibonacci numbers. We know which forms they have. each time asymptotical. Now let us look at those so Fibonacci number expression. Each one term is larger than 1 by modulus, and it is growing exponentially at large n. The other one is smaller than 1 by modulus, and it is going to decrease exponentially as n grows. So the second term actually at large n we can neglect. And then we can say that at limits of large n, now let me write, keep it on one screen here, maybe, and I have some empty space here. So n goes to infinity, fn is going to approach 1 divided by square root of 5. And 1 plus square root of 5 divided by 2 to the power of n. Okay, so exponential, it is exponential function now, and we just need our fractal dimension is going to be is divided by how much the number of boxes grows as the size decreases. Each time we decrease by a factor of 2, so our dimension is going to be, the fractal is going to be log of that base 2. Log base 2 of log base 2 of 1 plus, did it already start malfunctioning? Log, yeah, it did. Log base 2 of the expression, what was that? So so updating didn't help. Let me see again. And let us hope it won't crash so soon. Now again. 1 plus square root of 5. Divided by 2. Or you can write in terms of a natural logarithm if you want, a logarithm of 1 plus square root of 5 divided by 2 divided by a logarithm of 2. All right, so is everything clear, everyone? How we do it? And yeah, as a side result, we learned how to solve recurrent equations. So if you have linear recurrent equations, we had here of the second order, because Fn was related to Fn minus 1 and Fn minus 2. So we have quadratic equation. If we have a third order, then you have cubic and so on, exactly the same way as you have as you need to solve characteristic equations in case of different linear differential equations with constant factors. Now, if you want to do it in terms of mass dimension, then what you need to do, let me show. you need to say that, okay, this full fractal set here is a sum of two fractal sets. One is here, and the other is here. So total mass is the sum of those two masses, but this has, if this has size 1, this has 1/2, and this has 1/4. And so now, if you put in there saying that the mass of a fractal set is the size to the dimension of d, and then obtain actually the same equation what we got here for Fibonacci's. Did you get what I was saying?
No, I got 1 plus 2 to the d equals 4 to the d.
Okay, let us do it that way, because also then the homework is fully solved. This here has size 1/2. This here has size 1/4. Now, according to match dimension, 1 to the dimension of the d is the full mass, is equal to the mass of the left part, which is 1/4 to the power of d plus 1/2 to the power of d. And now you need to solve it. How to solve this equation? Do you know how to solve this equation?
I mean, I did it and I got an answer that doesn't look at all like logarithm
okay.
1 plus square root of 5.
So let us see. This guy here is now did it again. No, luckily no. This is 1 divided by 1/2 to the power of 2d.
Okay, and you get there very quickly.
Yeah, and now you get quadratic equation. If we denote this guy here as x, then you obtain equation 1 equals x
Yeah. Okay.
square plus x. Okay.
What I did is I multiplied by 2 to the power of d, and then you get 2 to the power of d minus 2 to the power of minus d.
All right.
So then you turn that into e to the power of logarithm of 2 times d minus e to the power of minus that. So that's where you get the arc shine.
And at the end of the day, your answer might be the same as this answer here. That's why I initially didn't reject it immediately, but said that we need to check the numeric numbers.
Yeah.
Okay. All right, now you've got the both solutions. And we can move on. Next topic, what we have been doing during the previous years was sub and super diffusion, which is well, basically what I'm doing now is we go over to transport in non-smooth velocity flows. So with this, I close the topic of passive scalars in smooth velocity flows, and now we go over to passive scalars in non-smooth flows. So let me write it here as well. Now I already showed you this video earlier. From video, this is actually from paper originally, but let me show you again. Now I share another screen. And yeah, so that's how it looks. That's how it looks if you have some passive scalar in turbulent velocity field. Here you see that, as we discussed, that we have here regions with almost constant passive scalars, and we have regions with very fast variation of the tracer concentration. So I mark those regions with a constant, almost constant, mark with circles, and I also mark here with something which is called matured fronts. Matured fronts means that we have, if we speak about temperature falls by almost an order, or the same order of magnitude as the overall drop from left to right. And it's the dimension at which it happens is almost the smallest available scale, so-called Bachelor scale. So now, yeah, before we go on, I think we need to discuss a little about the scales available. So a large scale is clear. Let us enjoy a little bit this figure here, and then I start drawing and writing down what I am telling. So what is here, actually, this temperature field has been obtained using a numerical simulation. A numerical simulation involving so-called Greitner flows. I think I already told you a little about Greitner flows. These are delta correlated in time, which means that each next velocity field happens almost each velocity field survives for a very short time and then is switched over to the other. So if tracer is in a field, you have at each moment of time you have certain streamlines, but tracer particles will not manage to move much about those field lines, only a tiny bit, and then you switch over to the next streamline. And so because of that, there are some things what you need to keep in mind if you want now to match this kind of velocity fields to real velocity fields, but this can be done. So matching can be done, and I think this is worth discussing with you, because if you stumble upon some papers doing with Greitner flows, then it's useful to know the correspondence between those two. And now this one here, as said, is done for Greitner velocity field because it's quite easy to do. Just generate random field and then keep it only for a short time. Let each of the tracer particles move a little, and then generate randomly a new velocity field. So you won't need to do any direct numerical simulation to obtain real turbulent velocity field. That makes it easier a little. And the other benefit is that you exactly know what are the statistical properties of the underlying field. If you have something coming out from direct numerical simulations, the field has itself is clearly more complicated than that artificially generated velocity field, what you use in the case of Greitner flows. And now this aims to match real flows, and real flows are characterized by Kolmogorov turbulence, which means that you have certain fixed statistical properties, in particular how the velocity changes if you go from one point to another. And And more specifically, it appears that the velocity field in case of Kolmogorov turbulence changes in velocity components scale as it differ if we take two different points at velocity field. But maybe it's time to start writing down because I'm telling and nothing written down, so it's difficult to follow, I guess. Let me now finish showing this, switch over to again back to the whiteboard. And let us start writing down. So, analytical. We have turbulent spectrum. All scales are present in velocity fluctuations. You can say that we have vortices of all the sizes present. Now, this we can characterize in terms of what is known as Hurst exponent. We can characterize by the Hurst exponent. And now, first thing we need to explain what is Hurst exponent. Let us move step by step towards those tracers in non-smooth velocity fields. First, we need to know what is the Hurst exponent. And so Hurst exponent was actually initially suggested for the flood levels by a guy named Hurst. Originally suggested to describe Nile flood level fluctuations. And so what it means? It means that if we have, let us say we have a flood level Z as a function of time. And then I consider two moments over there, Z T minus Z E plus T minus tau. And now let us take, for instance, square this and average. We can average over T here because T is, we have the full time series, so we can fix T, fix tau, and study how this depends on tau. And now, if this is a power law, then we say that H is the Hurst exponent. Now, Brownian function, you can already tell what is your Brownian function Hurst exponent equal to. Who can tell me? Half. 1/2, yeah, because for Brownian trajectory, Z T minus Z E minus tau squared average is 2dt. 2d T, okay? This means that H equals 1/2. Because exponent here is 1, T to the power of 1, right? So 2H equals to 1.
Tau?
Ah, yeah, sorry, tau, yeah, sure. Thanks. That's tau, definitely. Not T, but tau. Okay, now I understand. Sometimes the cursor doesn't work, and that's when that a zoom window is over, but I am not seeing zoom window here. So okay, anyway, I'll fix it now. Oh, there's a power one. All right. Now, in the case of Kolmogorov turbulence, if our z is actually, we take velocity component Vx, for instance, Vx as a function of t minus Vx t minus tau. So yeah, roughly speaking, let us take now is tau to the power of 1/3.
Do you want to square the modulus?
Yeah, if we square it, 2/3 becomes. Yeah, now, okay, let us, here is important point, but let us just for the time being, okay, you see, first I took to the second power, and now I took to the first power. And of course, the result also scales respectively. So if it was first to the power of 2h, now it is to the power of 1h. So, but let me try to write a little better. First, I think it's better to move everything to a little to the side. Put it here. So we can say that our first exponent is 1/3 here.
Not,
but
2/3? 2/3?
No, because I take first power modulus and first power. That's what if you take here square root here, you obtain tau to the power of h. So this exponent here is just h.
Yeah.
So now, but here, as you see, as you saw, I took different exponents before averaging. In the second place, I just didn't. I should have written, of course, here also the averaging signs. And let me maybe just for the completeness do that as well. So let me move again this back and. And yeah, let me add here these brackets denoting averaging. And now, yeah, I took different exponents before averaging. And now the thing is that as long as you have so-called a Gaussian function, then it doesn't matter. Now, let us go to the next page, actually. And let us, a small topic now is Gaussian versus non-Gaussian statistics and functions. If velocity is a value increment, we speak about velocities, yeah. So if Vx right, before actually I wrote t, but I would have been also x here. Actually, it would have been better if it were x here, and here would be x plus certain displacement. Actually, not x but coordinate. Radius vector and r plus certain displacement vector rho. And then that would be proportional to modulus of that rho to the power of first exponent h. Okay. So I wrote here for time dependence, and that's also valid, but it's better because it's both the same scaling in space and time. So it's better, more instructive to take this as a function of coordinates. Both are described by first exponent. And yeah, let us take now just to keep one component Vx. And if Vx component x, let us say, minus Vx at x plus certain rho has Gaussian statistics. We say Vx is a Gaussian function. And
what does it mean to have Gaussian statistics? To be normally
so
distributed?
if you write a PDF, probability density function. So here is, okay, let us denote this as delta V. Okay, this is by definition is delta V. And now we have here probability of delta V, having delta V. And now here is the value of delta V. And now, if it is something like that, it is normally centered around 0. If we have a symmetry, up and down symmetry, then delta V is has the same probability as a minus delta V. And then we have here certain standard deviation, sigma. But that sigma is related to that rho. Sigma is function of actually rho at the displacement where you consider velocity changes. And now whatever power you take average, so you can say that delta V x. I dropped the delta V to the power of n average by modulus. It's certain numerical prefactor multiplied by sigma to the power of n. But sigma is dependence of rho is sitting in the sigma of rho to the power of n. So whichever power I take, this exponent goes linearly with n. In this case. Because we have the Gaussian tails drop off very fast. So you won't have any anomalies associated with the fact that we might have very seldom very large jumps in B. But we won't have them in the case of a Gaussian distribution. And so any nth power of increment average is just the standard deviation to the respective power multiplied by a numerical prefactor or the order of unit. Does it sound like?
So it doesn't have to be normally distributed.
No, it doesn't have to be normally distributed. It can be normally distributed. But we won't have any anomalies associated with the fact that we might have very seldom very large jumps in B. But we won't have them in the case of a Gaussian distribution. And so any nth power of increment average is just the standard deviation to the respective power multiplied by a numerical prefactor or the order of unit. Does it sound like?
So it doesn't have to be normally distributed.
it doesn't need to have, but that's what we call Gaussian functions. And that's quite important thing because, you won't need to specifically to have a Gaussian fall-off, but you still need very fast fall-off. If you won't have very fast fall-off, then you would have that, and that's, I'm going to write down also, you would have something which is called multi-affine functions. These are described by structure function scaling exponents, but that's what exactly what we're going to talk now. Oh, quite soon. Anyway, so if we have Gaussian distribution of increments, then there is only single Hurst exponent what we need to have. Everything is described by that. So if we go back to previous slide, then as you saw, I just arbitrarily took first I average second power of the increments of z and said that this is going to be tau to the power of 2h. And later on, I took first power of the velocity differences and said that this is going to be now tau to the power of h. Just proportionally to the power what I have at the, I take the increment into. Now, let us write this down. So, structure function scaling exponent. Structure function scaling exponent. So let us say, speak for instance about velocity increments, what I spoke about. So we can take delta v to the power of a modulus and to the power of n, and then average. And delta v here is defined as v at x minus v at x plus rho. So it depends on rho. And if this is proportional to certain, this is called structure function. This is structure function. And if this scales as rho to the power of xi, let us say xi n, then that xi n is called structure function scaling exponent. Now, if we have Gaussian function, then we have psi n is n multiplied by the Hurst exponent h. So basically, we need only one exponent to describe this. On the other hand, if we have essential non-Gaussianity, then xi n is a nonlinear function of n. So how nonlinear it is basically reflects how a non-Gaussian the function is. It means that you won't have, instead of having a Gaussian distribution, this is Gaussian, you would have something which has long tails. So maybe something like maybe power or at least non-Gaussian tails over there. So in that case, so-called fat tails. And those fat tails are important in many cases. For instance, if you go into stock prices, these are also can be described by such kind of structure functions, and they correspond more or less to h equal to 1/2, but there are quite significant fat tails. These are like you can market crashes within one day. You may have very large drop, for instance, in the market indices. So fat tails are important because they can describe crashes or some extreme events, and you need to be always be prepared against the possible extreme events. And yeah, any questions thus far? All clear?
So the function before was Gaussian. The what was the no, the 1/3 factor from before, that was a Gaussian function.
1/3?
The one with Hurst exponent 1/3. That was a Gaussian function.
You mean here in the previous slides? Here?
Even one more. Yeah.
The first one. Here.
The Kolmogorov turbulence.
Kolmogorov. Oh, right, yeah. So now if we speak about velocity, then yeah, let us move on. Basically, it means moving on. Now, in the case of Kolmogorov turbulence, velocity is slightly nonlinear as its dependence. And what we actually exactly have is that the third order structure function is equal exactly to 1. The others are actually, so I wrote here 1/3, but that's approximately. And now, yeah, let us move on. And this is so-called famous Kolmogorov results. One of them is like exactly that the third order structure function expressed in terms of velocity, the energy dissipation rate, but Kolmogorov, now whatever years there are, Kolmogorov turbulence xi of order 3 is exactly 1, meaning that v x minus v x plus a modules, or even without modules, cubed average scales as just a to the power 1. And the others are strictly are not strictly linear function of n, but the nonlinearity is relatively weak. So you have something here is n, and here is psi n. So here is 1, and here is 3, and it goes maybe something like slightly curved, very slightly curved. Still, guys are working on it. So Kolmogorov initially suggested this as a simple scaling law. Later on, he realized that actually it is not. He himself realized that he actually you need to have a spectrum of exponents, so a structure function scaling exponent. Propose modification to his own theory, and then people are there have been several like semi-empirical models trying to derive those so that psi n of n dependence. But because the dependence in nonlinearity is relatively weak, so it in most cases you can quite almost, well, depending on the application what you consider, you can neglect. In some cases, of course, because it's related to extreme events, extreme velocity drops, in some cases you might not be able to neglect it, but in most cases you can. And we are also going to discuss one case when you cannot, but in most cases it's quite enough to just to take linear consider Kolmogorov velocity fields like mostly Gaussian or close to Gaussian, and neglect that what we call also multifractality or multi-affine multifractality. Multifractality is another thing what another way you can describe such behavior as now we describe with structure function scaling exponent. So structure function, maybe I write like this, it's easy and it will not crash. So non-Gaussian fields need to be described not by one exponent H, but spectrum of exponents psi n. Now, another way to look at it multifractality. But I myself have found that multifractality is a little less straightforward, and I think maybe we can skip for the time being that multifractality. Multifractality, well, I can briefly speak also about multifractality, but multifractality. So what multifractality does, if, for instance, if you consider something like energy contained, energy fluctuations contained in a region or something like that, and then we characterize each point in space in terms of certain singularity exponent, like how each point let be energy let be sub a x the energy contained in a box sized a as a function of the position of the point, as a function of the position x of this box. And we say we try to we hope p a x is proportional to a to the power of certain alpha, but the alpha itself is a function of x. Okay, and then we consider a subset. We consider a subset of points x defined by alpha x equals certain alpha, a fixed value alpha, and ask what are the such points where the singularity exponent alpha equal to the fixed value. And then we expect this to be fractal set characterized fractal set in X space in the coordinate X space characterized by fractal dimension D. d as a function of alpha. And then d of alpha is called multifractal spectrum. D alpha is called the multifractal spectrum. So now, and then you just or try to calculate it using some mathematical techniques somehow, and then you present the d of alpha curve. Now, why I personally don't like it is that saying that p, look at this line, p of the problematic is this one here. So we expect each point in space to be described by certain scaling exponent, but normally the scaling laws appear only after averaging, and here we try to describe single point with some scaling exponent. Well, it's not a nice scaling law, and that's also it comes out from mathematical techniques, shows d of alpha curves, but because it's like in my opinion, so multifractal formalism is a little bit too mathematical and departs from physical content of it, because in reality you cannot say that okay, this point is characterized by that singularity exponent alpha, because in order to have exponent alpha you need to have averaging, and you won't have that if you consider a single point. So, in my opinion, also the structure of functions and multifractal spectrum describes the same thing. The structure function scaling exponent is my shoulder. So this is formally introduced by Mandelbrot. Formalism introduced by the Mandelbrot. But the structure function scaling exponents are much older, like introduced by Kolmogorov already. These are more easier to interpret. The meaning is clearer in the case of the structure function scaling exponent, and I personally like it. Now, okay, let me write off this down. This is some spam. Now, what I was going to write that the structure function scaling exponents and multifractal vector from describe the same thing, non-Gaussian. Non-Gaussianity. But in the context of turbulence, at least, you mostly use the structure functions in the context. Turbulence, usually structure functions. Okay. Any questions regarding those structure functions?
Since you drew this as a mathematically concave function, like sublinear, let's call it function.
Yeah. Normally it's sublinear because
it's a thin tail. It's an extra thin tail.
Which tail?
Thin.
thin. Well, Gaussian is as thin as it can be, and if you make it even thinner, nothing will change. It will be still only one single Hertz exponent in that case describes. So you cannot make it curved. It's other. It's only well. If we look at this dependence here, then so what does it mean that xi of n grows slower? Or maybe you can make it, but let us think. Let us think. What does it mean? Basically, is that in the case of turbulence, it's definitely that way only. So it means that if you take large value of a, that scale what you consider very large, then you have just a large scale amplitude what is in there, and that won't change much. But if you reduce a, then like if you go back, for instance, that picture what we have here, let me share it again over there as well, over internet as well. And so if we take this figure here, for instance, then you have if you go to smallest scale a, then very seldom you have very large these drops, delta T here in this case the temperature drops. So mostly you have very small drops, and sigma standard deviation, if you calculate, is very small because of that. In dominating, it is like that. But very seldom you have those very large drops, and now if you average a second power, it won't change much. But if you average higher power of n, then C will start introduce increasingly large contribution to the average value. And so as a result, the structure function, n-order structure function, will decrease slower in the case of large n's as what would you expect based on the second order structure function. I don't know. I'm not really sure if you understood what I meant, but okay. Let me write down it on the white screen and not just talk. Maybe you can make it clear at the point of it, the point what I was saying. So now. So suppose we have a PDF, something like that. PDF of increments. B, and here is delta T, temperature drop. I didn't make capital T. And now we have something like that, and then we have long tail. Okay. And now if we take delta T, but this guy here depends on the scale actually. So this is now when we have let me try to make it better. I rather write once again and have more space, and I draw on the same graph two PDFs. So one is here. Here is delta T. Here is scale. Here is the here is P, and the other is delta T. Here is probability, and here is delta T. And now we have a large scale. A is big. But in large scale, you won't have so so scales are not so significant because it's like you have input temperature input scale, and it cannot be more than temperature fluctuations. Input scales cannot be larger than you put in, and you put in something more or less Gaussian. So at the large scale is more or less close to Gaussian. But now if you go to the very small scales, so this is a big. Now let us make another curve where A is small. Now, because our scale is small, of course, the temperature drops are also smaller. Now you have something like that, but now here you have tails. Now you have big, these are tail, fat tail. Okay, and now we ask how the different structure function scales. So here is certain delta t delta t1, and let us here is delta t2. And here for with red, let me write here delta t naught, delta t0, delta t0. Now, if we speak about structure functions for the large scale, so a structure function of n of any order, it's basically that because we have Gaussian more or less distribution, any scaling structure function is on the order of delta t not to the power of n, right? Because it's more or less Gaussian. Now, if we take this small scale, then S, let us say S2 is more or less dominated by the more or less Gaussian part. So this is about delta T1 to the power of 2. But S, let us say 6, now because we, by taking higher order, higher power before averaging, so larger increments, larger delta T's contribute relatively more. So that will be now already go like delta T2 to the power of 6. Okay? This is roughly speaking, qualitatively speaking. So now where is our scaling exponent goes out? It's a ratio of scales. If this is scale, let us say here is scale 1. A is 1, and here is A much smaller than 1. Okay, and then we have a staying exponent saying that xi n in the case of let us take xi2. Xi2 it goes like A to the power of xi2 is about this divided by that. Delta T1 divided by divided by delta T naught squared, because of the second power, right? So S2 is delta T1 squared at scale A, and at scale 1, S2 is delta T naught squared. So if we expect power law, so A to the power of xi would be the ratio of those two, which is delta T1 divided by delta T squared. Now, if we take xi 6, then A to the power of xi 6 is delta T1, delta T2 divided by delta T naught to the 6th power. And now, if those ratios were the same, then of course just xi2 would be 3 times xi6 would be 3 times xi2. But now because delta 2, because delta T2 is larger than delta T1, so the ratio here is actually larger, meaning that xi6 is smaller than xi6 is. I'm right. Just a moment, let's fix that. So I cannot write if my something from my Zoom overlaps with the region of on the whiteboard. So that's I already understood. xi6.
Excuse me, quick question.
Sorry?
Yeah, I didn't fully understand why we suddenly switched from doing delta T1 to delta T2.
All right.
So I guess going back when you say S2 is approximately delta T1 squared, and then S6 is delta T2 to the sixth. Why do we where does that come from? And then same logic for when we're looking at xi.
I'm not sure if I understood your question, but let me try to explain what how I understood. So if we take second power average, like we speak about second order structure function, then we won't put too much emphasis on large increments. In second power is not that high power, and so dominating those scales is temperature increments which dominate mostly those structure function, which is the average value of delta T's. This is just more or less something like half bits of the distribution, something like that. On the other hand, if we take higher power average, so this is essentially means weighting with more weight the larger increments. And if you have Gaussian distribution, there isn't much larger increments at all present. But if we have fat tails, then there are some. And meaning that if we increase the exponent of the structure function, then we put more and more emphasis on larger increments. So we put larger increments, so it means that's like dominating the delta T, which mostly dominates to the structure function, is larger than what we had in the case of second power. So in the case of sixth power, we put more emphasis on larger scales, meaning that the typical structure function is also large. So actually, you can look it also from a different point of view. Inequality between different averages, like harmonic one is the smallest, followed by geometric, and then first arithmetic average, followed by root mean square. You know that, right?
Yeah, this is making sense.
Yeah.
Thank you.
So now one is smaller than the other, but the differences are normal. It depends what are the data at hand. If all the numbers are the same, then all the averages are also the same and equal to the number. Now, the larger the difference between the numbers, the larger will be the higher order average. The second order average is larger than first order, sixth order is larger than second order. If we have Gaussian, the difference is sixth order average is larger, but not much, just a little bit. But if you have fat tails, it can become much larger. And now how much it becomes larger depends how fat are the tails. This is like another point on it. So what I try to do is just explaining about the scales with the values of delta t, which most contribute to the average. But on the other hand, you can also just look in terms of those inequality between the averages. And so what we obtain at the end is that if you take the higher order averages, the higher order average is larger than the lower order average. So let us. I'm not sure, Toma, did it help, or did I answer your questions or not quite?
Yes, thank you.
Okay, anyway, what we obtained now is that Xi6 is, because of that, Xi6 is smaller. No, wait, isn't it right? Xi6 is smaller than 3 times Xi2.
Why is it smaller?
Because A is smaller than 1. I assume A is much smaller than 1. Yeah.
Right.
And so that's why you have normally this structure function curve is curving down. Now here is also one of the homeworks what I have been usually giving to try to calculate some structure functions. So to try to get some data. And now I think in my previous, and you probably will find also some link in the lecture notes to the data available. But now I have already been having my own weather station at home, and you can try using those data from there as well. For instance, daily temperatures, and take daily temperature differences, like 1 day, 2 days. You could take also hourly, because it samples a 2-second frequency. You can 2 minutes frequency. You can take temperature differences between 2-minute data, but then you need to somehow to limit and not to go beyond a daily pattern, because you would expect to have some kind of random function, but you have over daily scale you have already days warm and night is cold. You won't want to see that pattern over there, so you need to limit yourself to a few hours. That's one possibility. The other possibility is you take average over the day, and then look how the daily temperatures vary. Then again, you cannot go to too long time scale, like 1 year is too much, because then you see monthly, yearly pattern. But if you take 1 month or maybe 3 months during summer, you won't see seasonal pattern, and you would be probably able to see something which looks like those what we call self-affine function. I haven't still mentioned, but that the Brownian function and velocity as a function of coordinates are called self-affine. But okay, let us talk about a little later. Let us finish about this numerical task. Let me write it also down. Homework. Download meteorological data. Earlier, I suggested ocean temperature. Ocean temperature. There are publicly available data. You need to send requests, and then they will send you download link. Temperature or air temperature. And try to get structure function scaling exponents. And yeah, let me write the link for my weather station. Okay, let us have a look what is over there. Yes, okay, here so here are some graphs, but you can obtain here.
We don't see a thing.
Daily data, and this is quite a long file. Okay, I'm not sharing just a moment. Sharing failed. Screen sharing failed. Okay. Still not working. Now it works. Okay, let us go back. So here is that the web page for what I gave you link, and you have here some graphs. You can actually here look also on the temperature graph. So this is 1 day pattern today. This is 3 days. Below you can see also daily data, daily averages here. And also for the year, we are having it somewhere from the December last year, so almost full year now. But then you can download here a daily raw data, and then you can pass through those. So here are different numbers, but there are at least one of so okay. So this is legend is here up. Time step, temperature, humidity, dew point. You can actually dew point is also probably somewhere. Yeah, dew point is one of the largest. You could try both temperature and dew point is also kind of interesting because in this graph here, the light blue is the dew point graph. Dark blue is temperature graph and light blue is dew point graph. Both would be something like those random Hurst exponent described functions. And have fun playing with this data. I think that will be quite nice exercise. Not too difficult numerically. Python will help you. Okay, and you can see then try to see if it is single exponent is enough, or maybe it's not essentially non-Gaussian. You need a series of exponent of those higher order structure functions. And link to that web page I provided. Yeah, if you like cats, you can also look here. Just the web page itself has a lot of cat pictures. But yeah, for you, this is just the data what you need to look at. And now let's go back to the previous screen. And okay, yeah. All right, so here is a link. You can download some raw data from there, and then you can play with. You can try getting a structure function scaling exponents for temperature. Either at 2-minute frequency or for daily averages. Or for daily averages over with one day frequency. Yeah, and now regarding which structure function scaling exponents make sense to calculate, actually the order number, there is no sense to take too large order number because in order to have a good data, you need to have good average. But as I said, if we increase this order number n, you put more and more emphasis on large events. Large temperature drops. And these are become increasingly seldom. You increase n, you put more emphasis on very large temperature drops, and as an end result, the higher order structure functions become less reliable statistically. So normally you wouldn't exceed n 6 or 10 if n not larger than 6 to 10. Well, you can look and you can try something like 8 and 10 to see if you can get it more or less reliably. If not, then you just keep until 6.
There's nothing saying n should be integer, right?
Yes, nothing says it should be integer.
What about negatives?
You can take also negative. Normally, usually people use positive, but actually negative also is a possibility. So n close to 0, it means essentially geometric average, right? As the limit n approaches 0, you obtain geometric average. Totally thinking about it. Never thought about it?
Why are we raising to the 0th power? What is going on?
Zeroth power average is geometric average. At the limit, n goes from positive plus 0. That's the limit. N goes to plus 0, you have geometric average. Think about it.
I'm just saying myself averaging 1. What is 1 average?
Yeah, but
it's
it's limit. It's not just okay. You can think about it later. No, but home bike is clear, right? And there are still we have been here now talking about 1.5 hours. Let us make a small break and continue after the break. So how many minutes? 10 minutes? 5 minutes? How much? Normally we had quite short break. 10 minutes. Okay, 10 minutes break. Right, I think we are more or less. We can continue. And yeah, actually, there are two ways to calculate structure functions. What I showed you before was by modulus of increments. Delta t. What is it? Somewhere at the beginning. Here. Yeah, I put, as you saw here, I put modulus signs.
We don't see it.
Sorry?
We don't see it.
Oh, why don't we see? I reconnected that eclipse here. Okay, now you can see. There are two ways you can calculate delta t, and one is by modulus, the other is without modulus. In which case, if you take odd number structure function like order number 3, then one, then yes, the result will be much smaller than because it is symmetric. If PDF is symmetric, the result will be strictly 0. But if it is not symmetric for this or that reason, then the result will be not 0, and you might have another scaling exponent which describes odd number structure functions with signed quantities. Now that's also, we'll return to this a little later, and then you see, you understand also why sometimes it makes sense to calculate those odd number structure functions with sign. Now, before going on, let us go back to those videos here from last time. I'm using those last time videos to just to show, because otherwise I would need to dig out papers, but now I have, because I did it last time, then I have them available here. Okay, so this one here, right? Yes, there are two. Now, this is empiric, all empirics, calculate structure functions. And I started with velocity in structure functions, and then I showed you the slightly curved graph for the velocity increments, and saying that Kolmogorov is close to true, but sometimes you need to take into account certain Gaussianity and slightly curved, slightly nonlinear dependence on structure function scaling exponents. But when we go to temperature, for instance, passive scalars, then the intermittency is much more significant. And there are somewhere later here, I have also some pictures from certain papers. Let me see. Okay, here, this one here. What you can see here is a structure function, how structure function scaling exponent. Oh, right here it is denoted by zeta, not psi. How structure function scaling exponent depends on the index, now here denoted as p. Unfortunately, there are no numbers here, but actually the bold line is 1. The top is 2. And at the bottom, the marks ticks goes over 2. So this first tick is at p equals 2, next tick is p equals 4, and so on. So you can see here that the structure function scaling exponent for the temperature of passive scalar in Kolmogorov turbulence is much more curved, and it will not go. It will go up very slowly, and almost as if saturating somewhat. And now there are two theories. One is my own, and the other is guys from the paper which I showed you before, with the color fixture with the temperature fluctuations. One theory says that in the case of structure functions, you have so-called mature fronts, which means that structure function actually saturates to a certain value. The other theory, what myself made is saying that the structure function scaling exponent for the passive scalars grows logarithmically. And here are, in this graph, what you see are results from different papers, different research papers, all marked with different symbols here on the graph. And the black line is my own theory, which grows logarithmically. And it seems quite nicely to fit those experimental data, actually. And I have my own numerical simulations based on a certain simplified simulation scheme, which are blue dots, I think. No, these are not blue dots. Anyway. This I don't remember. Anyway, the question is whether this logarithmic growth or saturation growth, practical differences are not very big because either way, as said, you cannot calculate too large with too large structure function scaling exponents because your statistics becomes not very good. And if the index is not very big, the difference between a logarithmic dependence and saturation dependence is not that big numerically. So more precise simulations are needed actually to understand who is right and which model is right. Now, let me explain you briefly both things, that the mature fronts and my own theory. So regarding mature fronts, even I go back to that colorful figure here before, where I marked also different parts. So we have here in blue, in green, I marked something what we can call a mature fronts, segment of mature front. And now let us try to estimate that's the limit of very large temperature, very large structure function index P or N. Previously, in my slide I wrote it as N, but here on my paper actually used P, different index. So let us consider how we expect the structure function scaling behave if we have mature fronts. That's the limit of very large order number of structure functions. So in that case, as we said, if we increase the structure function scaling exponent, then I start making increasingly more emphasis on the largest available temperature increments. So basically only those mature fronts. And now, as you can see, that mature fronts is quite convoluted like a fractal line. And so we say that, okay, we have mature fronts. At each resolution, we can downsample this whole picture into a smaller resolution, and we can still see the mature front, but in less details. And in each, if the mature front has a temperature drop equal more or less on the order of magnitude of the global temperature drop, then the temperature drop over the mature front is independent of the resolution of the map. And so let me now start writing a little down on the whiteboard. So let us try to estimate the structure function scaling exponent now.
Resume
It says it's screen sharing is paused. Some on the other hand, I can see what.
There's a button next to it, resume. There's a button to resume it next to it. Next to new share. Resume share, it's green.
Oh, resume share. Okay, all right. Okay. Thanks. Now, and so we are now trying to calculate structure function scaling exponent at very large index. Sn. If we have mature front, a piece of mature front, and now consider we have a coarse grain, so the resolution is at which I can take this is resolution is A. Here is A. Okay. And then we have here more or less delta T global temperature drop was the order of magnitude here. Now structure function scaling exponent, we say that this is now dominated by that those mature fronts, meaning that the average value of delta T to the power of n averaged over all the field is estimated as that global temperature drop delta T global to the power of n, and now saying that this dominates means that we neglect all the other contributions and multiply here the number of cells n where we have mature front divided by number of cells in total what we have. Is that clear what I'm doing? We are saying that it's a structure function, high order structure function with n goes to infinity. It's dominated by the mature fronts, meaning that in these structure functions we can consider only the mature front pixels and say that temperature drop over the at the scale A. This is at the scale A. Is estimated as the total temperature drop to the power of n and the fraction of cells where we have mature front. But because whenever we have mature front, we have temperature drop on the order of delta dg. So is that expression clear more or less? From it came? Total? Not really?
I don't really know what the mature front is.
Oh, I tried to explain. The mature front, we call mature front. Let me go back. And so on this figure here. So mature front is temperature front. What you can see in this figure, but not any temperature front. You can see a lot of temperature fronts. For instance, here is one temperature front. Here is another one. But these are not mature fronts because there is temperature drop is big, but not very big. So here is the biggest. And you can say that mature front is defined as those temperature fronts where temperature drop is on the order of global temperature drop from left pole to right pole, like by a factor of 2, let us say. Differs by a factor of 2 or something. Okay? Is it now clear what is the mature front? Yeah. So here I marked mature front with a green line here. If you look carefully, you can see here with green line marked what I found here as something like a mature front in this figure. Okay. So elsewhere there are temperature drops big and large, but here is the biggest. And if we consider the limit of the structure function limit for large n, then we can say that only the largest temperature drops contribute, and so he estimates the structure functions. A function as a global temperature drop multiplies the relative fraction of the mature front cells. Okay. Now the number of mature front cells. Now the question is how this scales behave. Structure function describes how this what depends on A we have. Delta TG, this has no depends on A. Depends on A is sitting over there. So in mature front cells, now this is estimated as. Now, what was it again? It was scale A to the power of minus D, fractal dimension, right? Sorry, number of fractal set from box counting definition, the dimension. The number of boxes of size A needed to cover the fractal set, and also A to the minus D. Number of total cells, of course, is proportional to A to the minus D, the dimensionality of the space. Here D equals to 2, in that figure we have two-dimensional figure, right? Now, because of that, our structure function, delta T, let us put modulus here also, delta T to the power of n, average, is estimated as now delta T global to the power of n and A to the power of D minus df. Okay, and as you can see, here is the that guy here is now our structure function scaling exponent psi, and it does not depend on n, so it is reaching saturation. So increase n, but that psi doesn't increase anymore because there is no dependence on n right now here. Okay, so if you have mature fronts, then it means that structure function scaling exponent saturates. And yeah.
It also has the shortest possible tail because it's bounded, so it has no tail.
Yeah, it is, but it's truncated at very large value. So if you compare with the standard deviation, the ratio is very large. So there is still long tail, which at the end of the day is truncated, but it's still very long at fat.
Mm-hmm.
Because if you look back, if you go back again to that figure, then the middle part of the PDF is dominated by those very small temperature variations, those flat regions. So delta, typical or most probable delta T is very small here. And so mature friends also, it is truncated over there, it is truncated at a very large value. So we do have long and fat tails. Now going to the to my model. My model actually tries to explain why do we have actually those mature front-like things, and I might as well show here because this figure here is from my paper, and suppose we start with the same situation that we have hot ball and cold ball, and look here at the bottom sequence of figures. And so let left be cold and right be warm and color coded. And now suppose we have some large vortex here in operation, and this will distort at large scale things. But now, yeah, the exponents here are written in terms of Greitner exponent size. This is a little different story. Let me redraw in whiteboard and just explain the same thing over there. But before going, I use this figure here to qualitatively explain, and then I do math a little later. So we have big vortex, and then we have one of those smaller vortexes. So first, the big vortex. deforms globally, brings somewhere those certain temperature isolines, isotemperature points closer to each other, but somewhere they go depart from each other, but somewhere they are brought together. And now at next stage, a little smaller vortices step into play, and they bring them those parts which were already brought close. Those smaller vortices bring them even closer, and then and so on and so on. So at the end of the day, there are points where some that black and white here are brought actually to contact basically. And this happens in finite time because each next vortex is, let us say, 2 times smaller and a certain factor of times faster. So smaller vortices turn around faster, right? Because large vortex also velocity differences are larger, but the size of the vortex is even larger. So the rotation time, hydrodynamic rotation time of the vortex for small vortices is faster. So this first step, bringing working of large vortex is really slow. Next one is faster, and then so on and so on, faster and faster and faster. And this is a geometric series. And sum of geometric series where each next time step is certain times smaller than previous is a finite. So you can those 2 lines are brought into contact in finite time. And so we have a set situation when we have certain points are brought into contact basically in finite time. On the other hand, of course, there also happens at small mixing at the very small scales, and maybe at small scales there are some smoothing happening. But well, fundamentally, this is the reason why you have somewhere you have a very large temperature drops, and there are regions where you have no temperature drops, because the geometric series of vortices basically can bring any 2 apart points into contact in finite time. Okay, and now I am not going to explain exactly how the model ended up in logarithmic dependence, and that's not really that much of so important here. So it's that would need more time to do all those mathematical model implications, discuss also model implications and mathematical steps. Let us discuss a little more that geometric series what we have here. And now I stop this here and go back to whiteboard. And so yeah, it's the same thing what we had now on whiteboard, on the video, but now here. So vortex of size A. We said that velocity magnitude of that vortex scales according to that Kolmogorov turbulence law, which I'm going to derive later on. Just using already that result, it scales a to the power of 1/3. And now rotation time tau A is estimated as the distance traveled divided by the speed, and so this goes to a to the power 2/3. And so if we have now one temperature isoline, cold, and then we have warm or hot, and now one vortex brings them here together, somewhere here, and then somewhere it departs them. So this time needed here, let us say this is scale 1. 1. A equals 1. Okay, so this is unit time now. Yes, this tau one is divided by estimated as and let's say that this as unit speed. V1 is also defined as 1. We can always define our units. We are free to define distance unit and speed unit. So let us define distance unit as 1 for the largest vortex available, and speed unit let be defined by the speed of the largest vortex available. So and tau is scale divided by speed is also unit. Now if we take next vortex, A equals 1/2. Okay, now sorry, this goes here 1/2 and then another 1/2 here. So here scale A is 2, 1/2. And now tau 1/2 is 1/2 to the power of 2/3. And so 1 tau 1/2 nth generation is 1/2 to the power of n and multiplied by 2/3. And here we have total time now, tau total needed to bring this line into contact is sum over tau n's is sum over of 1/2 to the power of 2n/3. And yeah, well, this is on the order of unity. So this happens in finite time. Tau total finite. So we can bring two temperature lines into contact in finite time. That's how it works. All right, any questions?
Are we looking from half to half?
You remember how we made a gauge graining our different orders of magnitude. So we take the order of magnitude, if we increase by a factor of 2, it go to different order of magnitude, which differs by a factor of 2. So it's gauge graining. We gauge grain a process over different scales by a factor of 2. You can take factor of 3 or a factor of 1/2, it doesn't change. Either way, you have geometric series. So it's if it's a factor of 2 or a little different factor on the order of unity, it doesn't change. To conclusions. Okay, now few things to discuss. First is that Graham model. And this other is so-called Ramp-Cliff structure of temperature increments, and which is related to the odd number structure functions. Let us first discuss the Graham model. Graham model so in that case, we say that velocity correlations at certain moment, at certain coordinate r at certain moment of time t, correlate when now take correlation with v at another point r prime and t prime. They are delta correlated in time, which means that it is 0 if t is not equal to t prime and is non-zero if it is if t equals t prime. So we write something like a certain d as a function of r minus r prime, and if it is isotropic, then we can put here also modulus sign, so it depends only difference between those 2 points, how far they are, and the Dirac delta t minus t prime. Shift some, so that I can fit it better. I need to better calculate how much space my expression will take to always displace. Dirac delta function t minus t prime. And now the question is, what is this guy over here? So if we have power law, like we expressed from the in the case of Kolmogorov turbulence, then that would be also a power. D of rho would be proportional to rho to the power of psi. And now, yeah, I think that's the reason why I used that for structure function previously zeta in the paper and not psi because psi was used here for this exponent here. Okay, because now we already used psi, let us make it alpha. Okay, but now that alpha here is not the same alpha as in the case of Kolmogorov turbulence. Like in Kolmogorov turbulence, we expect velocity differences go as a distance to the power of 1/3, which means that if we take second power, like here, it would be maybe 2/3 or something. But let us see what is over here. Instead of like mathematical idealization of zero correlation time, it is more instructive probably to think about very short correlation time. We do have correlation time, but it's very, very short. And then what does it mean? It means that our particle, our material point of particle, massive laser particle, moves with velocity field, and it's somewhere. It's somewhere, and then now in velocity field it moves. But actually consider pure particles. So here is one particle to the frame at rest. This is reference particle, a particle which we use as a frame, and the other is which moves relative to that reference particle. And then relative speed is just depends on this correlation term here, d. So suppose now this goes as velocity here, v is on the order of distance. So this here is distance r. This goes as r to the power of 5, according to this correlation. And but now, because the velocity correlation time is very short, the particles manages to move only a little bit. So velocity is v, but it travels to distance v times tau, where tau is correlation time, and this is very small, much smaller than the distance r. And then next velocity field steps into play. And then next step is taken, and some in random direction. And then next one and next one. And all these steps are in the same of the same order of magnitude as long as distance does not change. V scale is estimated as distance to the power of alpha. And now we ask how long it will take for the particle to increase the distance by an order of magnitude, by from R to R, let us say. How long it will take? Long it will take for the pair of particles to increase distance twice. But this is like diffusive process, random steps, random short steps, right? Isn't it? So the answer is that T multiplied by the diffusion coefficient T is should be square root of dt is R. This is a condition. If the diffusive travel distance is on the order of R, then the distance between those two particles can increase by a factor of 2. And now let us plug in. Well, first we need to know what is diffusion coefficient. But you remember, the diffusion coefficient is step length squared divided by time. Okay, let us open new page. So R is square root of dt. Now d is v times tau, correlation time tau squared divided by tau. Is now, but v was a function of distance. So v is now it is R to the power of 2 alpha because it goes to square multiplied by tau, right? And now T time needed T is estimated as R divided by D, R squared divided by D is estimated as R to the power of 2 minus 2 alpha. And that is still that tau divided by tau. Okay, tau is very small, and actually because tau is very small, here we need to also have a very, I dismissed here a brief factor certain that the v is only proportional to the 2 alpha, but something like multiplied by v naught square, and v naught square. Let us keep that v naught square as well. Here is also constant. So we have v naught square. Let us rewrite it again. V naught square divided by tau and multiplied by R to the power 2 minus 2 alpha. And now tau goes to 0. But V naught square divided by tau is finite. So in the Greichner model, the correlation time goes to 0, but V naught square divided by tau remains finite. So we have is effectively a diffusion coefficient which depends on the scale, and the alpha which comes out from the correlation of the velocity field in Greichner model as exponent alpha is now related to the time it needs to for the distance to increase by a factor of 2. And now what we want? We want our real velocity field to match the Greichner model field, because Greichner model is really something aim to make something mathematically tractable on the one hand, and on the other hand, still it needs to match somewhat reality. And now, what happens in reality? How depends the time tau t for the distance to increase the time needed to increase the distance by a factor of 2 on the distance, but that we already know in real flows. So in Greitner flows, now T is estimated as V naught squared divided by tau and R to the power of 2 minus 2 alpha. And so alpha is exponent from the Greitner model. Now in real flows, T is estimated as a scale R divided by velocity at scale R, but this is proportional to this R to the power of 1/3 over on R to the power of 2/3. And now we need to compare this exponent and that exponent. So now we see that we must have uh, 2 minus 2 alpha equals 2 over 3, which means that 2 alpha equals 2 minus 2 over 3 is 4 over 3. Okay, so that Greitner exponent alpha is 2 over 3. All right, so you can match Greitner flows to real flows, but the exponent is different. That's the conclusion of the long story. So whenever you stumble upon papers dealing with Greitner flows and those scaling exponent of the Greitner flows, you need to keep in mind that that is a different exponent, and that is not really the Kolmogorov exponent, but 2 alpha is 4 over 3. The exponent there is 4 over 3, which matches the real flows in the case of Kolmogorov turbulence. Okay. So I understand that story here about now matching Greitner flows with real flows was maybe a little bit difficult to follow. I'm not sure. Was it? But let us keep the conclusion. Let us keep the conclusion that real flows can be matched more or less to Greitner flows, because at the end of the day, what matters is that in both cases, the distances between material points grow in the same way. Now, what we did, we obtained matching between Greitner flows and real flows, so that what would the exponent of the Greitner flow needed to be in order to have the same scaling of distance between material points as in the case of Kolmogorov flows, and that is 4 over 3. Now, how you feel about it? Did you catch it somewhat, or was it completely total? It was more or less? Okay. Not really. Toma, how about you?
Yeah, following okay. Quick question. You said on the line where you wrote in Greitner flows, then you wrote V naught squared over tau is what? I can't read what you wrote there.
Finite, yeah.
Finite.
So,
oh,
yeah,
okay.
finite, yeah, because that's how the Greitner flows are defined. You know, you see, Greitner flows are defined so that there is a correlation V R of V R prime, and there is a function D, and that D being finite basically means now. So how we obtain that? A Greiner flow is at limit of zero correlation time, and now you can it as having an infinite velocity, because well, Dirac delta function means that it takes infinite value when d is equal to d prime. Velocity themselves goes to infinity in such a way that the diffusion coefficient, what we obtained later on, that v tau divided by v tau squared divided by tau. Yeah, that's on the next page. So diffusion coefficient would be finite. So let us have a look once again. So because we have a very short correlation time, the 2 points which are separated in space but are subject to the same Greiner flow, they depart each other in a diffusing manner, because there is a very short correlation time. Each step taken of one particle relative to other is very short. And once it correlates, it's in a random direction. So it's a diffusive process, and this is characterized by diffusion coefficient equal to step length squared divided by step time. And if we have speed v, then step length is v times tau, where tau is correlation time. So v tau squared divided by tau is our diffusion coefficient. I've written down here. D is v tau squared divided by tau, that's diffusion coefficient, and that needs to be finite. In the case of Greiner model, we let tau go to 0, so that v goes to infinity in such a way that that diffusion coefficient remains finite. That's the main thing. And then this means also that v naught square divided by, maybe I somewhere messed up, I think it should have been v naught square times tau. I think I'm missing here somewhere tau. When I wrote it later on. Yeah, so that diffusion coefficient needs to be, probably it's better to fix it, because if I'm going to send you the screens, it's bad if we have here something missing. So let us see, diffusion coefficient is v tau squared divided by tau. Then I plugged in but tau is yes, that's okay. No, this is okay, because here you see that the tau times v naught square must remain finite. R to the power of 2 alpha is finite. Tau times v naught squared needs to be finite. Now, but how did I get that v naught squared divided by tau? Something was is messy over there. T is v naught square divided by v naught square r divided by d. Now I plug in d as tau v naught. Actually, that v naught is to the power of -2. I divide by d, but d has v naught to the power of 2. So if I divide by d, it goes to -2. And so here is also -2. And so, yeah, let me now correct this. That guy here is 1 divided by tau and v naught square, and v naught goes to infinity, tau goes to 0, but tau multiplied by v naught square is finite. Okay. Now I hope it's clear.
Yes, very clear. Thank you.
And yeah, probably I need to fix also here. I had a mistake from here. It's also minus sign over here. Yeah, I think this is really useful knowledge because nowadays, still up to now, people are doing Greiner model traditions of Greiner model, and then experimentalists read the papers on Greiner models and they don't understand what to do with it. So now you equip with this knowledge and you more or less you can match your experimental results with those Greiner model results. Now, what next? Yeah, I promised to speak about so-called Ramp-Cliff structure. And for Ramp-Cliff structure, still I think what I mentioned before, my own theory, I can briefly still summarize how it involves, and this helps a little bit to explain what the Ramp-Cliff structure theoretically, but first experimentally. Ramp-Cliff structure is the following thing. That suppose the same situation as we had before. We have hot ball and we have cold ball. And then there is a turbulence between, Kolmogorov turbulence. And now you have those mature fronts and plateaus of temperature and so on, everything. And now let us consider how temperature depends from hot ball to cold ball. Let us take axis from cold to hot. So x-axis from right to left. And now, okay, here is graph would go vertically, let me temperature. If we take one line going from left to right and consider how temperature depends on x, t as a function of x. Overall, it's a result of y, but we neglect right now y depends to consider only temperature profile along one line. And then Ramp-Cliff structure means that temperature grows from cold to ball, slow ramp, and then cliff. Oh, it's the other way around, sorry. Now I do that. Okay. We have here cliff, and then slow ramp, and then cliff, and slow ramp, cliff, and so low. Still, I drew in the wrong way. What I'm doing. So basically, it means that the cliff sign is the same direction as the global temperature drop. Temperature drop is from left to right. So this is average profile. The Ramp-Cliff structure means that we have behavior like that. So cliffs, so mature fronts are preferentially directed in the same way as global temperature gradient. Okay, that's what means Ramp-Cliff structure, also known as small-scale anisotropy. Ramp-Cliff structure. Structure, small scale anisotropy. Why on small scale anisotropy? So normally you would think that if there is a fully developed turbulence, there are a lot of vortices. And once, so it is the temperature, so that temperature drop, when it drops from left to right, this local is rotated so many times. It starts from large scale, then large scale rotates it, then smaller scale rotates it. Even smaller scale rotates the direction of temperature front. It turns so many times that intuitively you would think that if you look at the smallest scale, you won't see a global anisotropy. Global anisotropy is left is hot, right is cold. You would expect that because there are so many different size vortices, that if we look at the smallest available scale, you won't be seeing the direction where the global temperature gradient is. But the answer is small scale anisotropy means that actually that is not true. If you look at the smallest scales, the largest drops are still always or almost always in the same direction as the global temperature drop. No, yeah, maybe I can also write it down here. That the direction of largest temperature drops at the smallest available scale are still in the direction of the global temperature drop. Okay, so now that can be analyzed in terms of odd number structure functions. So if you take, if there were no global small scale, if there were no small scale anisotropy, then odd number structure functions would scale like drop off very fast. But now, because this, actually largest drops are still at the direction of the global temperature drop, they make increasingly big role in the case of the large structure function scaling exponents, and in the direction of in the case of smallest scales available. So you have anomalously small odd structure function scaling exponents. So basically the same thing that we observed in the case of structure function scaling exponents when we considered modulus, is that the large structure function scaling exponents are not growing linearly with n, but much slower. They remain much smaller. So here the same thing, that if we take a large n, so this structure function scaling exponent remains very anomalously small in that case. Now, about the model and qualitative explanation why that happens. The qualitative explanation comes out from my one-dimensional model to describe this thing. And let us go to another page and look at the some box where we have mixing taking place. And again, let us take here a ball, a hot ball, and here a cold ball. And now let us consider a certain isoline of temperature. And suppose it is initially straight, although definitely it's difficult to achieve the case when it's initially straight, but suppose it is straight. And now consider effect of a certain elementary large-scale flow. And the simplest flow is some kind of shear flow. So this temperature T equals to constant line, what it evolves into would be something like, maybe something like that. Okay, it evolves shear in this direction and that direction, deforming in such a way. Certain vortex moves in such a direction. And now we consider how the temperature profile from left to right evolves. Now take our axis here, and then temperature goes here until this point. It goes from up down. But now from here to here, it goes the other way around, because now here, here is, this is X and here is temperature. Now here, so this, if we draw here a set of isolines, so this was one isoline, but next one is going something like that, and the next one is going like that. So here we have a local maximum, local minimum, and here we have another local maximum. So it goes something like that. Temperature goes down, and then goes up, and then goes down again. Something like that. Does it make sense? After this action of shear flow, if you consider temperature profile, which was initially what was initially from left to down, straight down, and now it goes like that. And so we can build a simplified one-dimensional model of such kind of mixing and turbulence. That we have temperature profile initially goes like that, and now we divide it into 3 pieces, 3 equal pieces, and then we compress this 3 times. The new profile is the previous one, compressed 3 times down, up, down. I know what I did wrong. Down, up. I need to divide into 3. Sorry. Let it make okay, into 3. Long legs, I'm also getting a little tired and doing stretching here. Okay, so it goes now down, down. I want to do it in red. It goes down, up, down. Okay. So one single Monton's decreasing section is now substituted tripled. We see here we had, as in the previous figure, we had a first continuous drop from left to right, and now it was substituted with 3 segments, 2 of which are in the same direction from left to right down. The other is the middle one is reversed. Okay. And now that happens in each scale, actually. So this is the effect of largest vortex, but we have also smaller vortices. And so somewhere here, we zoom in and take here a smaller effect of smaller vortex, let us say like a region like that, and repeat the same thing. So we divide into 3, and then change also into 3 segments. Going up, down, down, up, down. Okay. And now let us look at where we have mature fronts. Mature fronts are in those places when we have always segment going down, right? Or going up, depending on the if we have increasing mature front or decreasing mature front. But there are always 2 downwards segments and 1 upwards. So now if we multiply probabilities of having all these generations, large vortex, a smaller vortex, even smaller vortex, if we multiply probabilities that having at the smallest scale, all the vortices having the same effect of having from up to down, then the probabilities of 1/3 and 2/3 they get multiplied, and it's much higher probability of having all the segments from left to up, from up to down, rather than otherwise, because the probabilities relate to 2 to the power of n, where n is a number of generations. So let me write it down. Yeah. The probability of a mature front. Mature front first. Mature front all the vortex generations, meaning different sizes of vortices. Vortices act in the same direction. Either from up to down, or the other way. Around. Now there are 2 times more up to down segments. So the probability, the frequency of mature fronts up to down is 2 to the power of n times larger, where n is the number of generations of generations. And this is a log base 2 of larger scale of the total global scale divided by the dissipation scale, which is a smallest scale. Okay. And so if there are many generations, so increasingly have actually more frequently, so mature fronts in the direction of the global gradient. That's like a qualitative explanation why you have a small scale anisotropy, why you have mature fronts in the same direction as the global gradient. All right, now what we did not discuss, but is still a good idea to briefly mention, and these are also in the earlier lecture recordings, are things called sub and superdiffusion, which are somewhat related, unrelated to what we talk today, but somewhat related as well. Because we introduced Hurst exponent. The Hurst exponent is quite often exactly used in terms of sub and superdiffusion. We have still something like 10 minutes to go, so let us briefly mention it. Briefly about sub and superdiffusion. So diffusion R square is proportional to the times the first power. And now subdiffusion R square prop 2 t to the power of 2h, where h is smaller than 1, smaller than 0.5. And respectively, superdiffusion is the other way around, h is larger than 1.5. Now you can ask why, in which cases you have super and subdiffusion. And the answer is normally subdiffusion you have when you have traps. I have I cannot, I'm struggling in getting a correct equality sign. The thing is that I have here my own keyboard. One of those keyboards I can use to get sign, but the other I can. Okay, now I got it. Now super and subdiffusion. Just see, it's either slower or faster than normal diffusion, and super subdiffusion happens when you have traps. Traps lead to subdiffusion. And what we can do is we can try to recall the very first lecture when I spoke about diffusion when you had array of vortices. When you had array of vortices, so a vortice is the paradox line, and then vortice is this and that way. And then we calculated here effective diffusivity. And then it was like Becquerel number, square root of Becquerel number, it depends, something like that. But now consider a little different situation that we don't have stationary state yet, but we let here, again, suppose some tracer put in on the right wall, tracer goes in. Tracer goes in, and now it starts propagating here, but it propagates can propagate far along the paradox line. But if it happens to move in here, it will get trapped, and so it can get trapped. And so now it appears that the time spent here, you can have long time being spent here, but you can also have short time spent here. So trapping time now, PDF of trapping time, is a power law. And in that case, this is what we call continuous time random walk, CTRW, continuous time random walk. Maybe I better type in because I kind of feel that my handwriting becomes less and less legible. Let me type in. Continuous time random walk. Walk. Yeah, if it is if the trapping time is a power law, if the PDF of trapping times is a power law, there will be a subdiffusion. And subdiffusion exponent depends on the that exponent of the PDF. H depends on the exponent of the PDF. That's how we can get in the most easy way the subdiffusion process. Now, one simple example actually for subdiffusion, which is mathematically kind of nice. If you like mathematically peculiar things, then you might like that. So we have now consider a plate. Here is a plate, which is, let us say, hot. otherwise, let's make it cold. So, and now let in here hot water stream. Hot water. Hot water. And now this here, let us suppose temperature in the bulb is 0, but here we have something which is larger than 0, T naught is larger than 0. And now we ask how that temperature will behave in space and time. And it appears that here you can obtain nice fractional derivatives, meaning that your equation which describes propagation along x-axis in the hot water stream would be something like square root of d over dt of temperature is certain coefficient here and d squared dt over dx squared. And in that case, the travel time needed to reach distance x. Let's say x scales as time to the power 1 over 4. So diffusion process would be 1 over 2, but here is 1 over 4, meaning that first exponent here is 1/2. If you are brave enough, you might try to see if you can get this estimate and obtain the same result that indeed here h is 1/2. That thing here, now do you know what is square root of derivative? So I could derive it as for you as well. If you want, I can kind of not very strictly, but a little bit sloppily, I can derive this equation here. But it will be not very long. So first thing next time, if you'd like. But before I go on, otherwise we end our lecture today. So what is square root of derivative? Raise your hand if you know. Toma, have you met non-integer number powers of derivative?
No, I don't think so.
Okay. So that's actually a very simple thing, meaning that squared operator. So you see, this integral differential operator, and the square of it is just time derivative. So by definition, a square root of a d over dt, if we square it, meaning that apply twice, it just is a normal derivative. And how you obtain now integral differential expression for that is if you take Fourier transform. You know that if you take a d of over dt of certain function of time, and now take here Fourier transform. Then this becomes I omega and f of omega. So basically, d over dt becomes multiplication by I omega, right?
So is it square root of I omega?
Yeah, exactly. And so square root of d over dt is just square root of I omega in Fourier space. That's it. Very easy thing. It looks not fancy. If you want to impress someone, you can write it, but actually it's not that difficult. If now you can write back and forth in Fourier space and obtain expression, and this is just integral kernel, a convolution integral kernel what comes out. But there are people who do it quite a lot, and mathematicians who work, in particular our department of cybernetics, our department here works with fractional derivatives, equation involving fractional derivatives and going solving inverse problems related to that. So some mathematicians out there who work with these kind of things. All right, but we are not going to focus too much on those fractional derivatives. Just to mention that one more thing, and other than that, I think we moved again quite successfully, meaning that it was probably quite stressful for you today as well. Mike is smiling, so was it a little? Okay, anyway, you have lecture notes. I emphasize important things, and the rest is less important. So even if you don't catch all the details, it's still okay. Just as long as you catch something about I don't. So I guess that's it, and see you next week. We are slowly catching up, maybe 2 more times, and then we can take again 2 hours lecture or something like that. We'll see. But we are catching up.
Maybe next time we can start with the physical significance of fractional derivatives.
Sorry, once again,
I said maybe next time we can start with the physical significance of fractional derivatives.
Okay, so you want to hear a little bit about fractional derivatives, right?
Yeah, because I see what it means mathematically, but I'm trying to understand what it could mean physically.
Okay, we'll talk a little about fractional derivatives here. And maybe a little more about, well, we spoke about subdiffusion, but we didn't speak about superdiffusion, maybe also a little about superdiffusion as well. So we start with fractional derivatives, then about superdiffusion, and then I go on with what's next up on table. So we are actually moving towards turbulence itself. We are actually now finishing the massive scalars and moving to vector fields, and well, next topic is actually magnetic dynamos, and then after that, magnetic dynamos are passive vector fields. Kinetic magnetic dynamo is a passive vector field, and then we move on to real turbulence, which is active vector field, mixing of active vector field. That's the plan. But we start with as mentioned, with fractional derivatives, superdiffusion.
Okay. Thank you very much.
See you next week.
Thank you. Bye.
Bye.